All right, the hydrologic cycle. This is something you guys have had many times, hopefully by now. Talked about the water cycle when you were younger, lower grades, however you want to say it. Hopefully a couple times, once, hopefully in middle school, grade school maybe even. You had earth science in high school. He may have touched on it there as well. And it's essentially, nothing's changed. But we might use slightly different vocabulary, we might have a slightly different focus than you had in the past. Water's pretty neat stuff. When I was in high school, I remember my teacher calling it the Mickey Mouse molecule. It looked, the way he drew it obviously made it look like the mouse ears. But those were the two hydrogens, and the face was the oxygen. This one still sort of looks that way, but a little more modern maybe, sort of grasshopperish too, I don't know. So two hydrogens and an oxygen, H2O, okay? It's a compound. We talked about compounds at the beginning of the semester, talked about how magical they are. You put two ingredients together, in this case two gases, and not only do they make something different, they make three somethings different, all right? And that, as I said, is something that's really unique for water. There's very few other things, if anything, I really ought to Google this one of these years, that exists in all three states of matter normally at the surface of the earth. Somebody tell us one of the states of matter, please. Liquid, good. What's another one? Solid and gas, beautiful. All right, and sometimes what? Plasma, yeah. Last I checked, which was a while ago, they were still kind of on the bench about plasma as to whether it was a very unique stage, give it a thing, or if it was just a hybrid, momentary kind of thing. I don't know that they've ever solved that. But we throw that in there as a sometimes why kind of rule. But solid, liquid, and gas are your three, okay? What do we call liquid water? Water, good. How about gaseous water? Water vapor, good. And we've got the frozen solid water. Ice. I give you a hint there. I said frozen. Yeah, ice. All right. Not that you didn't know that already. But and if you're lucky, all right, you'll see some questions as simple as that on the next test. Just because we do need to, call it what it is. It's nice when we don't have big fangled scientific words for everything. So, additionally, they didn't just paint it lime green and blue because it looks pretty. They're trying to indicate another neat feature of water here, the fact that it is polarized. All right, polarized as a battery is a great example. It's got a positive and a negative side to it. And what that allows is a really neat property where water loves to stick to itself, loves to stick together, kind of daisy chains through the process. And it, again, gives it some unique abilities. But so water molecules love to stick together because they're polarized. Water exists in all three states of matter under normal circumstances at the surface of the earth. Water is composed of two hydrogens and an oxygen. And I think that's everything we've said to you about water. So you always hear that we are running out of water. Oh my God, we need to conserve water. We don't have enough water. Water. Well, we live on a planet that's damn near 3/4 water. What's the problem? Why can't we use that water? It's salty, yeah. And why don't we just take this?
boil the salt out of the salt water.
So just gonna say, why don't we just take the salt out of the salt water and everyone can quit whining? Oh, well, there is that. I don't think we'd use it all, but well, in the end, it's a really simple, sort of dumb reason. It takes a whole lot of energy to do that. Small scale, obviously, people can do it. Evaporation nets, they catch. Well, that's not really desalinizing things. But there's a handful of ways to catch water. Vapor nets, I just said accidentally there. They put those up in places where there's a lot of fog and mist, catch the water and it drips down. But desalinizing, since that's what we were actually talking about, uses a whole lot of energy. And, God forbid we actually ever get to that point, we're going to do it. But it can be done small scale by evaporation. Because the neat thing about evaporation is only water evaporates. So anything that's dissolved in that water stays in the container, right? So the water evaporates up. We somehow force it to move to another container where it turns back into liquid and leaves all those nasty dissolved solids behind. Yes, ma'am?
I've never really thought about this before, but glaciers are fresh water, right?
Yeah, ish, yeah, fresh enough.
But they, like, in the Arctic and the Antarctic, wouldn't it be ocean water freezing to form them?
That's kind of the ish part. Depends. You've got a dividing line. I mean, it's in the end, all of our precipitation comes from the ocean. So it goes back to that. Did it fall as snow and refreeze, or did the ocean legitimately freeze itself and become ice? So it is a mix, and that's why it's like half and half. That is one of the problems, though, that we're having, because I thought you were going to go with, like, capture all the stuff that's melting off the top. Because we certainly could do that, too. Storage is a problem. We don't have an infrastructure set up for that or anything like that. But that's part of the problem, is when all that glacier ice off the top melts, it sinks right down. It's so cold, it's so dense, and it's not the same as ocean water. So it is a little different, but all right. So anywho, so we got a lot of water out there, but can't easily use it because it's salt water. So let's move to the land then, where we've got about 30% of the Earth's surface left. We call that terrestrial. Just introducing a couple words here if you didn't already know them: terrestrial and aquatic. Okay. So on the continents, we've got our fresh water, which is, and this is where they get their number from, about 3% of the total water on the planet. Right? So yeah, the majority of it is more or less unusable in its present form. We certainly could, we had to, and there's certainly a lot of money to be made if we figure out a great way to mass desalinize large amounts of water. So this fresh water is tied up in the streams and lakes. That's what we call surface water. And it's tied up in water in the ground, which we conveniently call groundwater. And it's tied up in ice. Okay? I'm missing one bullet there where we have, and I've left it as a conversation point, one more place on the planet where we have fresh water. Got groundwater, surface water, ice. Where else is there water? Yeah, in the atmosphere. Okay? Your clouds. Stuff that haven't even formed the clouds yet. So the atmosphere is another, I'm sure no one's bothered to measure the percentage. It's not a whole hell of a lot, but it's there. So that's what we got, okay? And this is all we've ever had. That's the other thing. That's what I really like to point out in the water cycle. Each teacher has their own little angle. My big thing is that it is a cycle. We had, I don't want to say one event where we got our water, but one main event where we got our water. I think you'll see that in a minute here. And short of an odd comet here or there smashing into us, we have all the water we've ever had and we're ever going to have. So it is a limited resource in that regard. It's fixed. So in my earth science classes, in my geology classes, at some point, we usually talk about the formation of the earth. In environmental science, we don't get to do that. So I'm going to try to nutshell this first bullet for you here. There was a point in time when the earth was forming. We're going back about 4.5 billion years ago or so, where the earth was forming, and it was basically just this molten ball in the sky. The whole solar system looked about the same at that point. It was just coming together. And picture some sci-fi movie where you're going to this fiery lava planet or something like that. It looked very similar to that, probably. So we were magma. We know that because, well, the inside of us is magma now. It's just the outside that's cooled off to a thin little crust that we've managed to survive on here. But underneath us, it's all still magma and whatnot. So over time, we know that we went from point A to point B. We went from this fireball planet to we've got a nice cool crust. Folks doing the math, working some physics, etc. We know that when things, and you guys even know this, when things get hot, they expand. When they get cold, they contract, right? So we put 2 and 2 together, and we figured out that as the outside of the planet cooled, it more than likely shrank a little bit, which led to cracking, and that cracking allowed more or less what we call worldwide volcanism. Not like pointy volcanoes, but picture a softball with the red stitching on it, or a baseball, all right? And these giant seams opened up. You guys probably know those from plate tectonics. But on day one, all right, we didn't have continents, we didn't have anything. We just had a rocky planet that cracked open, and this isn't day one, but it started this conversation. Out of that came a whole lot of water vapor. Again, we know that because today there is a whole lot of water vapor, water molecules, whatever you want to call it, mixed in with the magma that we still have. As it came out, again, just picture your typical volcanic explosion. All that thick, billowing stuff that comes out of a volcano isn't smoke per se. It's mostly water vapor. It just looks so dark and evil because of all the ash in it. So that goes up when water cools. I'm using a word we haven't talked about yet, but you probably know. It cools and it condenses, turns back into water vapor, right? And clouds formed, and it rained. And it rained, 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 and they're telling us that it rained long enough to fill the oceans, okay, eventually. That event is called outgassing. All right. Outgassing is an ongoing effort. As I said, every time a volcano belches out, we get more water vapor. As some senator was kind enough to point out, a volcano puts out more global warming gases in a single eruption than most cities do in a couple decades. It's absolutely right. Okay. But again, we can't control a volcano.
We can't control the city.
We can control our own expenditures. So there's that. And I saw you had a question. I'll get to you in once. I just want to finish this thing here. So that is the primary source, as most teachers teach it. The primary source is outgassing. The secondary source, as I mentioned a couple minutes ago, are comets. Okay, comets. You probably heard dirty ice balls. They have a lot of names for them. We talked about, perhaps, I mentioned all the craters on the moon in here once, maybe not. We have every reason to believe that we got hit just as many times as the moon did, if not more, because we're bigger, all right? And so more than likely we got pummeled, all right? There was a period in time called heavy bombardment. There was just way more riffraff in the solar system than there is now. And the beauty of that is once they smash into something, they're out of the equation, right? It's one less thing floating around. So things eventually settled down. But, short story long, some folks are trying to make an argument that our primary source of our water was comets, okay? And that is a one-time event, as I said, in the sense that there was that period of heavy bombardment. Yes, comets do still come by, but thank God they don't do it anywhere near as frequently as they used to. So we're calling that a one-time event. The problem with that hypothesis is that now that we've landed on a comet, we've tested comet water, it's a different isotope, for lack of a better word. It's different than Earth water. And we do find it in the oceans. We find comedic water. But the ratio is just not there to support that our primary source is comets. So on the test, when you see the question, and you will, primary source of the Earth's water is outgassing from volcanic events. Secondary source was comets. Yes, ma'am, you had a question, I think, about 6 minutes ago. I was going on. Did you have a question? I thought I said it. Yeah, you.
Yeah.
Okay. Questions about that? That was a whole lot of information that I usually have slides for, but I haven't taught environmental in a while, as I said, and everything else. This would just be a flashback of memory. It's hard to imagine it filling up the oceans. I'm with you on that one, okay? But we did have a lot of time for this to happen. This one you saw when we talked about the oceans, I think, a little bit. All right, this is just your lovely little water bottle example. We've got a couple water bottles in the room right now. It shows you, just that last sip at the very bottom, okay, represents all of the fresh water that we have on the planet available to us. And it's still not going to hold you responsible for the parts per thousand on the salinities, okay, so don't worry about that. Okay, so finally, if this is all the water we've ever had and all the water we're ever going to have, how does it all work out? Don't try to just start drawing this, but I do want you to draw a little picture in your notes. And what we really need, we need a sun, we need a cloud, we need a little bit of land with a tree on it, and then we need a watery area off to the land like we have here. Don't worry about all these dang arrows yet. So sun, cloud, tree, land, water. I'll give you a minute there to sketch that out while I inhale some coffee. So embedded in this arrow-infested diagram is a whole lot of vocabulary words. And that's why I kind of want you to have the option to sort of label this how you see fit. If you want to make a list of vocabulary underneath, and then maybe fill in the blanks in the diagram later, or if depends how quickly you take notes. If you want to label your diagram and define the vocabulary words all at the same time, it's your call. So it is a cycle, it is a circle. There is no beginning, there is no end when we talk about things like this, but there is a logical place to start. We just got done telling you that the majority of the Earth's surface is covered with the oceans, so let's start there. And we're going to have water leaving the oceans, going up into the atmosphere. That water is warmed by the sun, the very surface. And as we change from a liquid into a gas, we have that wonderful term there, evaporation. Again, a word you should be familiar with. We're just putting it into a context now. So the water evaporates from the sea, goes up into the atmosphere. Where it cools, because even though it's closer to the sun, the air just doesn't work the same way that the water does. Trust me, it cools off. And as it cools, it goes through another phase change. That phase change being condensation. Condensation is what we call gas to a liquid. So now we have all these little tiny drops of water up there in the sky, and those go together to form clouds. And that's one of the really big things that I need you guys to leave here with, because so many folks go out into the world thinking that clouds are made of water vapor, okay? They are liquid, water drops, or they are ice, crystals, okay? We've had a phase change from gas to liquid. And while we don't get into it, okay, because it's like for a meteorology class, it's super, 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 super important that a phase change is going on, because that's part of the movement of energy. And the water cycle is really about not just moving water, but also moving energy around the planet. And there's a word they use, latent heat. All right, latent heat of evaporation, latent heat of condensation. And again, please don't worry about that in this context, but that is going on in the background, and that is really what drives everything. It's the energy for all this to work. So we have to acknowledge that phase change. And, you know, in the end, it just bothers me when people think clouds are water vapor. So we try to fix that too. So we've got clouds. All right? And in this conversation, we need to blow that cloud onto land so that we can move on. The cloud falls apart eventually as the water droplets get too big to be held together by the cloud's own internal gravity. They're much more affected by the Earth's gravity, and the cloud starts to tear apart. Yes, it is sad. The sky is crying and the clouds are ripping apart, or you could just say it's raining. No phase changes, though. Okay? No phase changes. So that water falls to the surface of the earth, where it can do one of two things. It can stay at it can stay at the surface, and we call that surface water, or runoff is the actual word they use. All right? Runoff. Think of streams. Think of lakes. Okay? The runoff, and again, had we the time, I'm still pondering which way we're going to go with this. I think I'm going to give you two separate lectures. We'll have a whole conversation about streams and how they work. We'll have a whole conversation about groundwater and how they work. But to suffice it to say, they're the low parts of the land that serve to channel the water around. Okay? The other option, I said there were two things water can do. It could stay at the surface as runoff, or it can percolate into the ground and become groundwater. All right, we have the word percolation on there. We have the word runoff on there. Groundwater, again, is its whole own conversation. We talk about aquifers. You may have heard that word before. Those are vast storage pits of water in the ground. Okay? And as I've always argued with my old office mate, it all works its way back to the oceans eventually. And he argued that he wasn't just big picture enough. He says, well, no, it's going to go back to, the Mohawk, or it's going to go back to some other river system. But I'm saying eventually. And certainly in the case of this diagram, it works its way back to the oceans, where it evaporates, goes up into the sky, condenses as clouds, falls as rain, lands on the surface, stays at the surface as runoff, percolates into the ground as groundwater. You see that main part there of the cycle, okay? Now, obviously, there's more things on here, and some stuff that sadly isn't on here. Let's talk about the tree for a moment. Trees drink water, all right? And they use it for growing, for food, whatever, however you want to say it. But they also expel water, all right? Anything that has green leaves, green leafy matter, be it grass or leaves, whatever. And again, depending on your science background, you may know this, you may not. There's tiny little holes that open up and close on the leaves. They help you with photosynthesis, okay? Remember photosynthesis? We need to bring CO2 into the plant, and we want to get rid of oxygen. Well, we don't want to get rid of, but they get rid of oxygen, all right? It doesn't just sort of like fritter through the leaf. There's actually little holes that open and close for it. And yes, there's a word for those too, but you don't need another vocabulary word right now. Good job. Yep. While that's going on, water vapor actually escapes as well. Okay? And it's actually a pretty big part of the water cycle in certain parts of the world. Think anywhere you have a highly forested area, be it rainforest, be it just temperate forests up here. Because we don't really get that whole runoff part built in very well. Yeah, there's still streams in the woods, so on and so forth, but it's not like, well, maybe we get less groundwater. I don't know quite how to word the equation, but the trees are a huge part of it, okay? So they have a special word for that, transpiration. I forget what Raven, your textbook, does. You might see the word evapotranspiration in front of it, okay? But most folks have kind of decided that that's redundant because transpiration is a special kind of evaporation that leaves do. So to say evapotranspiration is, like I said, sort of redundant. What else is missing from this diagram? We talked about sources of water. One big thing missing here. Yeah, we could draw a glacier or an ice cap on there and have that melting, okay? And that actually leads us into a few more phase change vocabulary words. Let's catch up to the slides, though. All right, so 3 states of matter, 3 phases of matter, solid, liquid, gas. We talked about that earlier. As you move from one to another, it's a phase change. All right, so we got words for all these. Let's see what you guys remember. Let's play 20 questions here, or 7 questions at any rate. Solid to liquid, what do we call that? Liquefaction. Now, we're going to go with melting, but thank you. That's a great word. Liquid to solid. Not solidification. No. Freezing. We're in the context of water, so we're going to keep it fairly simple. There are, I'm sure, chemistry-based terms. Gas to liquid. We didn't talk about that one yet. Oh, yeah, we did, but gas to liquid?
Condensation.
Condensation. Good. We didn't do... Oh, there's liquid to gas. Okay. Liquid to gas. Did we do liquid to gas? You guys said evaporation? Or did I skip it? I skipped it, yeah. Thought so. All right, so the liquid to gas is evaporation. Gas to liquid, condensation. Sorry. All right, new one, possibly hard one. Solid to gas. No. No. Anybody else? Solid to gas. Mm-hmm. I'm really hoping you guys get it because it just jumped out of my head. Thank you. Yes, sublimation. Sublimation. S-U-B-L-I-M. Nation. Actually, just Asian, not nation. And then gas to solid. Usually, if you know sublimation, you know this one too. But. Deposition. Deposition. Which one?
Like, a deposition.
Not like salt or not like sediment or stuff like that. No, we do use that word a couple different ways. But gas to solid deposition, and everybody loves deposition because that's how we get frost. And you think about your water drops that you've seen; they couldn't possibly leave such cool little tracings that frost does. Again, we don't really have a whole lot of windows left in the world where you could do the feathery, beautiful Jack Frost stuff. But you may have seen it a few places here or there. Water drops are too big for that. All right, we need to come straight from the gaseous state to the solid state, and we get that wonderful, wonderful artwork. So deposition, sublimation, condensation, evaporation, freezing, and melting. And at the very bottom, I threw in the evapotranspiration for you there, the whole big word. But most days you just see transpiration. And again, that's a special kind of evaporation that only green leafy things do. So, just a little wrap-up slide for you here, just talking about water in the air. And that eluded me for a long time. I mean, I knew it was there. I just didn't really think to talk about it as such. So we've got a slide there. It's a great source of water vapor. Condensation nuclei is a new term for you, maybe. It possibly came up when we talked about the history of environmentalism and air pollution. Okay, because that's how you get the pollutants out of things like coal factories and whatnot. All those little particles that come flying out of there, they attach to the water vapor molecules. Okay, that's one of the weird little things about water vapor. Yes, it loves to stick together, but it kind of needs something to get the ball rolling, a catalyst, if you would. All right, and unfortunately, little sulfur particles or hydrogen particles or any number of things that are floating around in the atmosphere can serve as that condensation nuclei.
So water just loves sticking to things.
Yeah, basically. And then the whole clouds and precipitation conversation. All right. Put a little plug in for myself here. We do, if you need another science class and you want to talk more about some of this stuff you're hearing today, like the coming together of the Earth, or maybe a couple weeks on weather, check out my Earth Science class. Okay, we talk about all that and more. Water on the ground. Runoff. It's surface water. We got streams and lakes. Percolation or infiltration. They use both words kind of interchangeably. Again, it depends on the author. I tend to say percolation. With that, we're talking about aquifer or groundwater, and the term we use for groundwater typically is aquifers. And I didn't give ice its own slide. We're going to consider that water on the ground. You've got glaciers. And then you've got ice sheets or ice caps. Depends where you are. It's an ice cap if it's actually over land. It's an ice sheet if it's hanging out over water. All right. And that's a large chunk of, let's say, if you can picture Antarctica, a rough outline of it in your head. Not all of that is continent. Okay. What we've come to map, a large portion of that is ice sheets, stuff hanging out over the continents. Similarly, up north, the North Pole. Okay, there's no land up there. You guys are becoming more and more aware of that as publicity-wise. They're talking more and more about the fact that it's melting up there, that very soon we'll be able to cut across up there with our boats, which is going to save people a heck of a lot of money. Instead of having to go all the way around North America, cut through the canal there, they can just go straight up and around. I think it's a shorter distance, especially if you're coming from like China, Russia over there. It's melting rapidly, and there is no land up there. And as one of your classmates brought up earlier, there is a difference in the ice. And just again, touching on climate change for a moment here. So it really matters what you're talking about melting when they're having this conversation, because there's a huge difference between ice on land, ice in the water, and not just in consistency, but in effects. Think about your glass that's had ice cubes in it, right? Typically it does not overflow when those ice cubes melt. Their volume is already more or less accounted for, okay? Not to mention that ice expands when it's frozen. So water, ice takes up more space than water does for the same volume. So when floating ice melts, it's gonna have an effect, just not as big of effect as ice that's on land. That's not counted in the volume of the oceans. So when that ice melts, that's the one that really gets us nervous, okay? But it's still not good, when the sheets melt, when the North Pole stuff melts. So, but just so you know, there is a difference. All right, so like I said, just a little brief introduction that might not have seemed brief to you guys, but before we start the water chapters, we've got